students, welcome to our today's lesson on electrode potentials. I hope you're going to enjoy. Now, when a metal rod is dipped into a solution that contains its ions, then some of the atoms on the metal rod drop into the solution, leaving electrons on the surface of the metal rod. For example, if it was a copper rod dipped into copper 2 ions, then the reaction that takes place is that some copper 2 ions go into the solution, forming electrons on the surface of the copper rod. At the same time, the ions inside the solution begin to combine with the electrons on the surface of the metal rod, forming copper atoms again. So these two reactions continue until a point whereby a potential difference is created between the metal rod and the solution. That potential difference is what we call the electrode potential of that particular metal. Same case applies to any other metal. For example, you can see also when zinc rod is dipped into a solution containing zinc ions, the same thing happens. Atoms of zinc go into solution. At the same time, ions from the solution combine with the electrons on the surface of the metal to form atoms. So an electrode potential is created again between the solution and the metal rod. Now, it is not possible for us to be able to measure that potential difference. It is not possible to measure the potential difference, but it is possible to connect two. Okay, we call this one a half cell. We call the metal rod dipped into the solution of its ions an half cell. So we can only be able to measure the potential difference between two half cells. So we combine the two half cells, as we are going to see in the next diagram, and then we come up with a complete cell, which we shall call the electrochemical or voltaic cell. Now, in the diagram below, we have an electrochemical cell or a voltaic cell, whereby we have two half cells combined together. We have an half cell of zinc and an half cell of copper. When we talk about half cells, as I've said before, we are talking about a metal dipped into a solution containing its ions. For example, at the left-hand side, you can be able to see zinc electrode dipped into a solution of zinc nitrate. And on the right hand, we have the half cell of copper, whereby the copper rod is dipped into a solution of copper 2 nitrate. Now, the two half cells are joined together using a salt bridge. We shall talk about a salt bridge. Then we also have the metal rods connected using connecting wires. And the flow of electrons is from the left-hand side to the right-hand side. And therefore, the more reactive metal is the one which is normally connected on the left-hand side of an electrochemical cell, while the less reactive metal is on the right-hand side of an electrochemical cell. Zinc, being more reactive, goes to solution, forming zinc ions, leaving electrons behind, while the solution becomes more positive. Electrons flow from zinc rod into the copper rod in the other half cell. Copper ions gain electrons, forming brown copper metal. So at the end of this experiment, you realize that the side containing zinc undergoes a decrease in mass, while that side that has copper rod has an increase in mass because of the gain of electrons which combine with the copper ions to form copper atoms which coat the copper rod, increasing the mass of the copper. Now let us now look at the components of an electrochemical cell. Now the first component is two half cells that contain different electrolytes that have metal rods dipped in the electrolytes of their own salt. Then it also contains a salt bridge. And then we have wires that connect the two half cells externally. We also have a voltmeter that measures the difference in potentials between the two half cells. So those are the components of an electrochemical cell. Now, I had earlier talked about the salt bridge, whereby I said it consists of salts of potassium and sodium, because those salts rarely form precipitates, though that's why they are normally used on the salt bridge. Then the salt bridge is normally a filter paper which is dipped into those salts of potassium or sodium salts, normally sodium nitrate or potassium nitrate. Then the voltmeter, of course, is meant to measure the potential difference or the electromotive force between the two half cells. Now on this given diagram, we have an half cell of copper and an half cell of silver, and they are in 3D, so you can be able to see the colors of the solutions. And it's important to note that copper is more reactive than silver. That's why copper is on the left hand side and silver on the right hand side. So there will be a deflection on the voltmeter up there as the reaction continues, and that deflection is now the EMF of the cell. Now the observations that are made on the zinc copper electrochemical cell as follows. We have the zinc rod dissolving. Why? Because it is more reactive, it is the one that undergoes oxidation, the loss of electrons. Therefore, as it loses electrons, then it goes into solution and dissolves, and therefore there will be a reduction in mass of zinc. Now the copper rod increases in mass. The reason is because on the side of copper ions are gaining electrons to form copper metal. Therefore, that copper metal formed coats on the surface of the copper rod, increasing the mass of copper. Then there will also be noted that there will be a deflection on the voltmeter, meaning there will be some electrochemical electromotive force that is passing through the voltmeter. And then finally, the blue color of copper 2 ion solution fades. And the reason is because copper ions, which are responsible for the blue color, are being converted to copper solid. Therefore, the color of copper 2 ions will fade away with time. Let us now look at the purpose of the salt bridge. The salt bridge is meant to complete the circuit by making contact between the two solutions. So by being in contact between the two solutions, it completes the circuit such that if it is not present, the electrons cannot flow. Hence, no reading will be made on the voltmeter. Then, the other purpose of the salt bridge is to maintain a balance of charges or ions on both of the cells. So it also maintains a balance of charges or ions on both half cells. Now, In the zinc copper electrochemical cell, the voltmeter is expected to read 1.10 volts as the electromotive force of the cell. But that is not the case. The reading will be practically lower. If done practically, that reading will be lower than 1.10 volts, and the reason is because of the connecting wires, which have some resistance which has to be overcome. So that resistance is what makes the readings lower than the expected 1.10 volts. Let us now look at the voltaic electrochemical cell representation. So, how is it represented? So it is represented as shown in this diagram, where M is the metal rod of the first metal on the left hand side. For example, if it is zinc and copper, of course zinc will be on the left hand side. So you'll just write Zn solid stroke the solution of zinc. So you can write zinc ions aqueous. Then these two strokes represent the salt bridge. So it is from the solution of the first half cell to the solution of the second half cell. The salt bridge is connecting the salts or the solutions. Therefore, you shall have the next metal there. Here we are representing N. N is representing any metal. In our case, then we put our copper ions there, aqueous. Then finally the copper rod, which is a solid. We shall write Cu solid. So that is how we represent an electrochemical or a voltaic cell. Some points to note during the cell representation is that M must be the one with the highest reactivity. In the reactivity series, M is supposed to be higher, i.e. the anode. It is drawn first on the left hand side when illustrating the electrochemical cell. Then metal N must be the one lower in the reactivity series, i.e. the cathode, and it is drawn second or on the right hand side of the electrochemical cell. Illustration of an electrochemical cell of zinc and copper half cells. Now the zinc rod ionizes, dissolves to form zinc ions at the anode, according to the equation shown alongside. Copper ions, on the other hand, gain the donated electrons to form copper atoms or copper metal, according to the equation shown. Now when you combine both equations, of course you will eliminate the electrons and you are able to get the overall equation as shown in the diagram, and with the electromotive force at the end of the equation. Now there are some points to note when writing the cell notation, and one of those points is always show oxidation occurring in the first half cell. So oxidation is the loss of electrons, so ensure that it happens in the first half cell, while the single line represents the phase boundary where a potential difference develops in an half cell. So I have shown you earlier about the cell representation whereby there are some slashes. So the first single line represents the phase boundary where the potential difference develops in an half cell. Then also include the potential of the cell at the end of your overall equation. Represent the potential of the cell at the end of the equation.